Hello, Matthew, Ben, and myself, Caroline, looked into an existing gun detection model to evaluate and optimize it.
While neural network technology has advanced significantly in past years, there are still limitations in the applicability of image recognition and security measures, such as over CCTV or in real time for use by law enforcement. This is due to the imprecision of small object detection and the relatively long inference time for image detection. The use of neural networks in these applications could serve as a tool to decrease racial bias in high pressure situations, which is of particular concern in light of the ongoing Black Lives Matter movement. Due to the black box nature of neural networks, it is of particular importance to explicitly ascertain racially unbiased performance for these applications. In our literature review, racial bias was never a measure of performance reported for published gun detection models.
We decided to test if a publicly available gun detection model showed racial bias. In addition, we attempt to optimize performance measures through hyperparameter tuning.
Our hypothesis for racial bias is that there will be a difference in sensitivity and specificity between people of color and white people. We also predict that when we train our model on both real and synthetic data, it will outperform the model that is trained solely on real data.
For model optimization, we wanted to test changing NMS threshold, batch size, and learning rate. Non-maximum suppression is basically just a way to filter out certain boxes that are below a certain threshold value of intersection over union. By adjusting this threshold, batch size, and learning rate, we hypothesize that we will be able to increase average precision and recall while decreasing inference time. In particular, we hypothesize that lowering the NMS threshold will increase the amount of false positives while also maybe increasing true positives.
EdgeCase AI trained a model using the Facebook Detectron framework's faster RCNN architecture. From the input of an image, the first convolutional layer detects the presence of basic features such as edges and corners. Each layer combines the information detected by the previous layer to generate higher level feature detectors, such as a face detector. During training, the weights of these feature detectors are optimized. The model learns to extract the relevant features as a part of the training flow. The region proposal network then generates initial regions of interest to use as candidates. The classifier network chooses the true bounding box for the target object based on the convergence of regions of interest. To set up Detectron, we used an Azure virtual machine as we needed a decent graphics card and a lot of VRAM. We installed an NVIDIA graphics driver, several NVIDIA libraries, and PyTorch.
To train our Detectron model, we ran 90K iterations on synthetic images and then 90K iterations on real images. This was done with an NMS threshold of 0.7, base learning rate of 0.001, and images per batch size as 8. Training is a main area where we want to improve on, as we want to try adjusting hyperparameters to increase average precision and recall. For testing, we have two different models. One is trained on only real data, and the other is trained, like we mentioned earlier, on both synthetic and real data. Our dataset for hyperparameter tuning is 300 images.
Our training dataset consists of both synthetic images from EdgeCase AI as well as real images, which are obtained from Google searches and movie firearm databases. To build our race dataset, we collected 400 images evenly from 4 categories: people of color with guns, white people with guns, people of color without guns, and white people without guns.
A detected gun box that did not cover at least 50% of the gun was marked as a false positive. Shown on the slide are some examples of bodily false positives and one of an incomplete gun false positive.
Of the false positives detected, a majority were objects that were attached to the subject's body. There was a larger percent of false positives on body parts of people of color versus white people. However, the difference in proportion was not statistically significant.
In a comparison of false positives, false negatives, and true positives between people of color and whites, the model appeared to perform slightly better on images of people of color. The false positive and false negative rate was higher for whites than people of color, and the true positive rate was higher for people of color than for whites. From our preliminary results, we found that there was not a strong racial bias in any of our measures of accuracy. There was only a slight difference. Another interesting finding is that the model trained on only real data had more false negatives and less true positives than the model trained on both real and synthetic data, which indicates that training on both real and synthetic data is superior to just real data.
While we scored the images, we noticed a few features that often gave false positives. Some common ones were hands, shoes, and car windows. One example of this can be shown in the image, as the car window is considered a gun both on the left and right, and 2 false positives.
Our future directions will be tuning our hyperparameters. Beyond the scope of this class, we recommend establishing a specialized dataset where individuals of varying races are photographed in the same set of postures or actions, such as filling up on gas, identified to be problematic. This will enable stronger certifications to be made about the lack of racial bias in a model.